let's take a few moments to talk about torque and angular momentum. Looking at this DL, you might have felt a little bit overwhelmed. We just learned a bunch of equations for momentum, and now we have to learn a bunch of new equations for angular momentum. But in actuality, you've pretty much already learned everything you need to know. Most of the equations for torque and angular momentum are identical to the equations for force and linear momentum. The only difference is you have to calculate certain numbers slightly differently. Let's take this equation as an example. This equation says that the total angular impulse is equal to the average torque times the change in time, and is equal to the change in the angular momentum of the system. But we've seen an equation exactly like this already, just with forces and momentum. It says that the impulse is equal to the average force times the change in time, which is equal to the change in the momentum of the system. So the main thing we need to figure out is how we calculate torque. Once we do that, we should be able to use these equations in the same way as we use the regular momentum equations. As we saw in the previous video, torque depends on two main things: the strength of the force that is being applied and the distance away from the center of rotation that force is being applied. Let's look at an example that should be familiar to most of us: a bicycle wheel. A bicycle wheel rotates around its center. So when we're considering the distance from the center of rotation, we're going to be measuring from this center. The equation for torque is given here. There are three equivalent formulations of it. Notice it's not just equal to the force times the distance. Let's see why that is. If I were to grab onto this bicycle wheel here and pull straight out, would it start to rotate? The answer is, of course, no. The bicycle wheel is not going to rotate if we're just pulling on the wheel. But notice that we are applying a force to the wheel, and that force is being applied at some distance away from the center of the object. So there's one more piece we need: the line that connects the center of the wheel to the location of the force is known as the moment arm. If the moment arm and the force point in the same exact direction, or equivalently in the exact opposite direction, then there will be no torque. Let's try to draw out an example and see if we can calculate the torque. Let's suppose that we have this force acting on this wheel. We want to know what the torque is. To do that, a good first step is to always draw the moment arm. The moment arm is just a line that connects the center of rotation to the location of the force. I'm going to draw it as a dotted line here. The equations of torque say that if this force and this moment arm are in the same direction, then the torque will be 0. But we can see that this force and this moment arm are not in the same direction, so there will be some torque. How do we determine what that torque is? Well, to do that, we need to determine what the angle between the moment arm and the force is. Let's continue this dotted line a little farther. The angle that we're interested in is this angle right here. That's the angle between the force and the moment arm. If that angle was 90 degrees, then the torque would just be equal to the distance times the strength of the force itself. But this angle is definitely not equal to 90 degrees. Let's say that that angle is equal to 55 degrees. And let's also say that the radius of this bicycle wheel is 50 centimeters. So what is the torque? In order to find that, we just need to plug all these numbers in. The strength of the force is equal to 20 newtons. The location that the force is acting is 50 centimeters away from the center of rotation. And the angle between the moment arm and the force is 55 degrees. So the torque on this bicycle wheel due to this force is 8.19 Newton meters. What is the direction of this torque? Well, first, we have to consider which direction the wheel would start turning if this torque was applied. Hopefully you can tell that if we were to push on the wheel this way, it would start rotating counterclockwise. So in order to find the direction of the torque, we take our right hand, curl our fingers in the direction of the rotation, and our thumb points in the direction of the torque. So the torque, in this case, points out of the board. Notice, though, that I've written torque in a couple of different ways. I've also written it as R perpendicular times F, or R times F perpendicular. Let's see very briefly what that means. Let's imagine this as a drawbridge. This cable right here is holding the bridge here. If the cable were to break, the bridge would just fall down. We want to know what the torque from this cable is. The force from this cable points in this direction along the cable itself. One thing that we can always do with forces like this is break them up into an X piece and a Y piece. If a force points in this direction, then there's an X piece like this, and a Y piece like this. The drawbridge is rotating around this end here. What's the moment arm for this force? Well, it's just the line that connects here to here. Notice that line is in the X direction. In fact, let's just take this top of the drawbridge to be that moment arm. Because that line points only in the X direction, we find the torque from this force here based on the piece of that force that is perpendicular to the moment arm. In this case, because the moment arm points only in the X direction, the perpendicular piece of force points only in the Y direction. But what is that perpendicular piece of force? If you work this out with geometry, you'll find that the Y piece of this force is equal to the strength of the force itself times the sine of the angle that the cable makes with the drawbridge. So we're just back to the same thing that we did in the last example. It's just the strength of the force times the length of the moment arm times the sine of theta. It's the same thing with R perpendicular times F. Instead of taking the piece of the force that is perpendicular to the moment arm, you could also take the piece of the moment arm that is perpendicular to the force. Which one you use is sort of up to you. However, it will always turn out to be the length of the moment arm, R, times the strength of the force, F, times the sine of the angle between them, every time. You may need to draw some things into a diagram in order to see what the angle actually is. But once you've found the angle, you can always find the torque by just plugging it in. Knowing this about torque turns out to be super useful and super duper important when we're building structures. And we'll start to see how that comes into play in next DL.